The following video is for informational purposes only. It is simply the opinion and experience of myself regarding solar. It is not meant to be investment or tax advice. I am not an electrician. I am not and have never been in the solar industry. I am not being compensated by anyone to promote any products. It is always best to consult an expert before making any decisions regarding investments, taxes, and solar. This is a video I've been wanting to do for a long time. Now that I have 3 years of data to work with, I want to look at how temperature, humidity, UV index, cloud cover, solar radiation, and array angle impact my solar production and in some cases consumption. So let's get started. In this chart we see the relationship between average temperature and solar production. You can see the general trend is as the temperature increases, the solar production increases. This makes sense because the cooler temperatures occur in the winter when the days are shorter and more cloudy, therefore less solar is produced. The opposite occurs in the summer. However, this relationship is not as strong as you might expect. This is shown by the R-square value. It is essentially 0.41. This means 41% of the variation in solar production can be explained by the variation in average temperature. This leaves 59% unexplained. Here is the relationship between humidity and solar production. You can see there is essentially no relationship. Here is the relationship between UV index and solar production. This is a point by serial correlation because one variable is discrete and one is continuous. As expected, as UV index goes up, the solar production goes up. It is a fairly strong relationship considering UV index is a discrete variable. Here is a surprising relationship. It is between cloud cover and solar production. Most people, me included, would think there would be a strong relationship between these, but that is not the case. What we're looking at here is the percentage of cloud cover on the x-axis. The more cloud cover, the higher the percentage. You can see the general trend is as cloud cover increases, solar production decreases. This is what we would expect, but the relationship is not too strong. It produced an R-square value of 0.42, or 42% of the variation in solar production can be explained by the variations in cloud cover. This leaves 58% unexplained. So what could explain this? Well, one thing I've noticed since I've had solar is not every cloudy day is the same. Some days we have high, thin clouds and I can get good solar production, whereas other days we have low, thick clouds and I can't get very good solar production. Both days would be considered cloudy. So I would hypothesize that cloud cover thickness could be the explanation for this weak relationship. Here is the strongest relationship. It is between solar radiation and my solar production. It produced an R-square value of 0.84. In other words, only 16% of the variation in my solar production could not be explained by the variation in solar radiation. This is most likely due to the fixed nature of my panels, causing them to not be in the best position each day. If you're in the northern hemisphere, the best angle for your solar is to face south, is for your panels to face south. I have 4 arrays on my roof. 2 of those arrays face due south. The other 2 face due west. I want to see if the south-facing panels produce more, or the south-facing arrays produce more per panel than the west-facing arrays do. Then I wanted to see if it changes throughout the year. So all of this data is coming from my Enphase app. And I think you're going to be surprised with the results. As expected, the south-facing panels produce more per panel over the 3 years than the west-facing panels. What was interesting was the monthly data. The south-facing panels produce more for 9 months, but the west-facing panels produce more for the months of May, June, and July. During these months, the sun is high enough to optimize the west-facing panels. Now let's talk about my consumption. As we saw in my earlier video, my consumption spikes in the summertime. This is because it gets very hot in Corpus Christi and I have to use my AC a lot. Consumption can also spike in the wintertime during cold days. This is because central heat uses a lot of power. During a typical year, consumption will be high when the temperatures are both cold and hot and trough during the in-between periods. The yearly consumption curve looks like this. In 2021, my AC consumption was as follows. I kept the house at 80 degrees during the day.
When I would come home from work, I would lower it to 78. Before I went to bed, I would set it to 75. In the morning, I would set it back to 80. I also use the central heat a little during the very cold days. In mid-2022, I started to keep the house at 80 degrees all the time. This is because I got an off-grid AC system for my bedroom. I also found other ways to stay warm during cold days.
Therefore, I did not use my central heat and lowered my AC use by keeping the house at 80 degrees. Because I started this in 2022, let's eliminate that year and compare 2021 with 2023.
Here's the curve for 2021. You can see the typical U-curve. Here's the curve for 2023. You can see the curve is flattened in the winter and only spikes when the average temperature gets around 80. When I overlay the charts, you will notice the 2023 consumption is lower despite it being a warmer year. This other chart illustrates this clearly.
You can see the consumption was much lower despite it being 3 degrees warmer on average than 2021. So that's it for this video. If you have solar, are you seeing similar results? Let me know. Take care.